Here's one of the examples from the Pearson textbook, and I want to use it to talk about the logic that you're using when using proof by induction and the layout that you need to use when writing it out on a piece of paper. Firstly, I'm just going to move things around a little bit because having these headings on the side I don't like. So all I've done here is shuffle it around a little bit so that the important headings are in line. Now this, when writing out your own proof for a question like this here is almost identical to what it should look like when you write it out. Not just the look of the layout, but all the content as well. When writing it out, it's very tempting to leave out some of these bits, especially when you're judging through a load of practice and you feel like you're writing out the same thing over and over again. No, that's really, really important. I think it's useful to think what the point of doing this practice for proof by induction is. It's not really to prove that something like this is divisible by 4, because it's in the textbook. It's a question in the textbook. We know it's going to be true. I'm not completely bothered whether this is divisible by 4 or not. We're doing this for the techniques of laying things out nicely and convincing somebody on paper. Having really rigid logic so that everything follows through and it's perfectly 100% certain that this thing is true. Some of the bits that are common to accidentally leave out are this statement about the assumption and the conclusion, also the headings, but these bits of logic are easy to leave out. But without them, especially without that one, your reasoning doesn't follow through properly. We can't make a conclusion at the end about, in this case, f of k being divisible by 4, if we haven't stated our assumption early on. Actually, just while we're on this example, I prefer to write it like this. Instead of writing divisible by 4, use a bit of algebra, be certain. Divisible by 4 means it's 4 times some integer. And I think that actually makes it easier to make a conclusion at the end as well. So, for other examples, I've written out here a framework that you should be using every single time. Sometimes we don't have to write out the claim in an exam, that might be a waste of time, but in practice, if you want it in your book, then you can. But we want base case underlined, we want to write out our assumption, and we want a subheading for the inductive step, and we want a conclusion at the end. I'm going to do a couple of examples. Here's another divisibility one. I'm going to use the framework that I just told you. As usual with these videos, pause it, give it a go yourself first, writing out all of this layout. Okay, I'm going to do it, and I'm going to be really clear. Base case, we're plugging in n equals 1 into the expression. We've got 3 to the 2 add 2. I know what 2 add 2 is, but we're going to be really, really clear. There we go. That is 81 add 8 minus 9. That is 80, which we know is 8 times 10, but I'm going to write that so it's obvious that it's divisible by 8. I'm going to write true for n equals 1 with a tick. Great. Now I'm going to write out the thing that I'm assuming. I'm assuming that when we put k in here, minus 9, that is a multiple of 8. So it's 8 times something for an integer. There we go. Now, we try and prove it for n equals k plus 1. Let's plug k plus 1 in. To k plus 1. I'm just going to write it out in full first. It's going to be really, really, really clear. That's a theme. Now, another good reason to write this out, aside from you have to do it, is that we've now got this here to look at and see how we can use it. I want to be able to use this in here. I want to find something in this one, in order to sub it in and use it. I'm thinking the more complicated bit, I want to find this, the 3 to the 2k plus 2, in here. Let's expand that out. Well, we'd be left with, this has got a 2k plus 2 and then another plus 2. So this is 3 to the 2 times 3 to the 2k plus 2. And then all this other mess. We've got plus 8k plus 8 minus 9. I'll tidy that up in a bit. But we found this, and so I can use my assumption. I can say, well, this equals, 3 to the 2k plus 2. If we bring these bits across to the other side, that is 8m minus 8k plus 9 plus 8k minus 1. And again, I'm going to be clear, I'm going to write out that that's the step where I used my assumption. By the assumption. Definitely going to get full marks for this. Alright, and I'm going to cross my fingers that all of this mess is divisible by 8 again. So I think I want to write this out as, I can't be bothered doing 9 times 8, I'm just going to write 9 times 8n, because I think I'm going to factorise that 8 out in a sec. Plus, 9 times 9 is 81, plus 8k minus 1, that 81 minus 1 is promising. That is 8 lots of 9m minus 9k plus 10, because that becomes 80, and plus k. Now, I could combine those k's, but I'm in an exam and I'm short of time. We've got what we need. It's divisible by m, by 8 even. It's only divisible by 8, though, because this bit here is an integer. There we go. So I'm definitely going to write that. I'm going to write divisible by 8. Hence, true for k plus 1. We've shown it for k plus 1. It's divisible by 8. Hence, by induction, the claim is true for all integers. And we're done. My logic there follows through perfectly. I've got the assumption and I've got a conclusion. Hopefully, if you did it yourself, yours looks very much like that. I'm going to do one more example now with matrices. Have a go yourself again before I do it. Okay. Base case, plug n equals 1 in. I'm going to start with this right hand side. So I'm going to start with the right hand side. I'm going to write right hand side. RHS is, I'm sure that's got something to do with flowers as well, but in this case it's right hand side. We've got minus 3 add 1, minus 1, 9 and 3 add 1. Equals the left hand side, equals what we wanted it to be. So that is true for n equals 1. Now assume true for n equals k. Might seem tedious, but I'm going to write it out. We're assuming that minus 2, 9, minus 1, 4 to the k is this. So it's the same thing, but with k in. We have to write that out. We don't know that it's true for n, but we're saying that it's true for k. N and k, different things. So we need to write it out. N equals k plus 1. I think I'm going to start with the left-hand side this time. because I'm already looking ahead and seeing how I'm going to use this. The left-hand side, when n equals k plus 1, is this to the power k plus 1. If you've not done it yourself yet, pause it now, do it yourself, do it yourself. I'm going to use I'm going to look for what I've got. I'm going to look for how to use my assumption even. 4. And that is that there. Now what I'm going to write here, I've used my assumption, so I'm going to say that I've used the assumption to make it really clear. There we go. Now I'm crossing my fingers that when we expand these matrices here, it's going to give us what we got. You can't see this, but I'm using my fingers to line things up. We've got -2 lots of this thing. Oh, warning sign in my head, double negatives, double negatives, double negatives. We've got 6k minus 2. That's 9k. I'm just going to shut up again, else I'll make a mistake. There we go. Oof. Right, let's simplify that up and cross our fingers. Nice. And I'm going to try and factorise out k plus 1s in order to show that it's the right-hand side. So this, if I want a k plus 1, if I want a plus 4 and I've got a plus 3, I need a plus 1. And that's exactly what we need. That is the right-hand side of what we need. Great. Implies true for n equals k plus 1, hence by blah, 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 blah. Write out those things so it gets in your head. That matrices one there, that one seemed... Oh, that one gets into some algebra. If you want to do some matrices revision, I'm interested as to what that even means. We've got some sort of matrix which represents a transformation, and we're doing it n times, and it just becomes this, it's just the same as doing this transformation. Maybe you could dig into why this is the case, especially since this is linear. That's what I'm thinking. Oh, I'm going to dig into that myself. Anyway, that's not the moral of this video. The moral of this video is be really, 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 really clear and write out these things every single time.